see if my clicker works. Where is it? Did I leave it in my office? Oh no, here it is. Okay, so this chapter is concerned with the idea of a fluid, and just to make sure we're all on the same page, we're not going to consider any substances where it's really confusing about whether it's a fluid or not. But you can think of roughly a fluid is something that can easily deform into any shape, and it includes both gases and liquids. We consider those fluids. A book, under normal circumstances, we would consider a book a kind of solid, and a jello is kind of a confusing intermediate case. It kind of deforms a little bit, but it probably would leave some air gaps. So, we're not going to treat anything that's going to behave like jello. We won't be considering it in this chapter. Only things that clearly can flow freely all over the place. They don't kind of maintain their shape. We haven't had occasion to mention the idea of density in this class. Many of you have thought about density before, I'm sure. The average density, if I have a chunk of something, I have my water bottle and there's a certain mass of water inside the bottle and it takes up a certain volume, then we might say is the average density of that water, and the density doesn't change too much from one point to the other. Well, I'm having a tough time moving this here. Average density is the mass divided by the volume. So the more densely it's compressed in space, in other words, for the same mass, the smaller the volume you put it in, the more dense you have. Okay, and the SI units, of course, are kilograms per cubic meter. Something we're going to look at a lot in this chapter, of course, is water. It's the most common fluid that we think about. Of course, air is pretty common too, but we just don't see it as easily as water. And the density of water, many of you have memorized from your chemistry exploits as 1 gram per cubic centimeter, which in SI units is 1,000 kilograms per cubic meter. Now, 1,000 kilograms is pretty massive, but cubic meter of water, that's a lot of water. It's not surprising that the mass is 1,000 kilograms. There's a table of densities of different substances in your book. Not all substances are well defined. If you say wood, well, I don't know what kind of wood. Are you talking about balsa wood? Or are you talking about oak? Or so but for things that have a definite density like aluminum, 2,700 kilograms per cubic meter, so it's more dense than water. And we'll find out that that means it's going to sink in water later on, right? If you put, if I have a cube of aluminum, it's going to have more mass than the equivalent cube of water. And so it's happy to push the water out of the way. The water gets pushed up while the aluminum sinks because the gravitational force on that piece of aluminum is bigger. Notice that we can take this relationship, mass over volume is equal to density, and sort of invert it and solve for m. Okay, and we're often going to do that in this part of the course. And if I calculate the associated weight, so imagine I've got a certain volume of water, I multiply by the density, which is 1,000 in SI units, and then I want the weight of that water, I multiply by little g. And it ends up giving the formula rho GV. And you'll just see that rho GV appearing a lot in this chapter. And if you don't have it in your head that that's a kind of weight force, it looks a little bit confusing. So when you see rho GV, think of a weight. We'll just see it appearing quite a bit. Now, we were thinking here of substances where their density is pretty constant. In other words, even if you're in the ocean, you go to the bottom of the ocean, the density of water doesn't increase very much as you go down. It's a pretty much the volume, you might think if you take a certain volume, it gets compressed because we'll find out the pressure is really big down at the bottom of the ocean, but it's fairly incompressible. So the density of water kind of doesn't matter. As long as it's a liquid, it's very close to 1,000. Same thing for aluminum. It's really hard to compress aluminum. But that's not true for everything. And of course, gases are one thing that does compress when the pressure changes quite a bit. So the atmosphere above the Earth, here we're envisioning the density by, I'm imagining I can see little molecules of air molecules there. And as you get further away from Earth, there's less stuff on top, which is crushing the stuff on the bottom. and therefore they can spread out more freely, assuming the temperature is the same all the way up. And therefore, the density might not be a constant, but can be a function of position in space. More generally here, I'm imagining, oh, I've got a sphere, and in that sphere, it's made of a substance where maybe I can mix in a little bit of air. So I put a little, put little tiny bubbles of air. So it's very not so dense here, and becomes continuously dense over there. In the same way that this is atmosphere is very dense near the Earth, or relatively dense, and not so dense up in the upper atmosphere. Okay, so that's density. You'll need to know about that for the lab this week. Second concept is pressure. And of course, we've all heard of pressure and thought somewhat about pressure before. And we're going to define pressure, at least initially, as something pushing, usually a gas or a kind of fluid, pushing on a surface. And we can calculate the force magnitude on that surface. So, if you have a ball or something like that, and you may know that even though we don't notice it very often, there's a certain pressure of the gas around us here at the surface of Earth, and it's pushing inward on the surface of that basketball, whatever, right? And so we could divide up that surface into little bits of surface and sort of say, well, what's the little bit of force that's acting on every bit of surface due to all these molecules hammering against that surface over and over again? And divide by the area of that little surface, and that would give us an approximation to the pressure at that point on the basketball. We'll talk about why we consider it to be a scalar. The way I've defined it here, it sounds like it would have a direction, right? Because it's defined in terms of a force magnitude, but if force has a direction, there's a good reason that we treat pressure as a scalar. In other words, it doesn't have a direction to it. We'll talk about that. The SI unit, of course, is newtons divided by an area would be in square meters, so Newton per square meter, but we have a shorthand unit for it, which is Pascal. So SI units are pascals for pressure. And let's just calculate something easy and calculate the pressure here. So cylindrical beaker, I'm going to imagine it's a perfect cylinder on a perfectly flat table. And it's got a circular bottom of radius 5 centimeters and a mass of 0.5 kilograms. That's the fluid plus the beaker all together. Find the pressure on the bottom surface. So the pressure here, there might be a certain pressure here and a certain pressure there, a certain pressure there. And if everything's perfectly manufactured, there are no ripples in the bottom of this cylinder, then the pressure is going to be the same everywhere. And to find that pressure, I can just get the total force that the table is exerting upward on the bottom of the cylinder divided by the area of the cylinder, okay? And to go way, way back to chapter 4, I guess, this could have been an early free body diagram, right? What's the free body diagram for my cylinder filled with some liquid there? Well, the table's pushing up on it, gravity's pushing downward on it, the net force is 0, and therefore the upward force from the table is mg in magnitude. And therefore, the pressure on the bottom is going to be the force that the table exerts on the bottom divided by the area of the disk. The area of the disk is pi r squared, okay? So putting all the numbers in, we've got everything we need in converting that 5 to 0.05 for SI units to put it in meters, and then plugging everything in, we get 624 pascals. I'm just doing this to kind of get you used to the idea that we can express things in pascals, even though you may not be used to that unit. Questions so far? So in this case, we're sort of saying, well, that's the average pressure because I use the entire force of the bottom and divided by the entire area. Now, in some cases, the pressure can actually change from point to point on there. And we'll find out that that's true when we have fluids. Like if I have, well, if you just think about a swimming pool or something, right? The pressure is sort of modest at the top, just under the water on the wall of the swimming pool, but it gets bigger and bigger and bigger as you go down. So pressure can be a function of position. It's not usually constant. So here's just a cooked up way to think about how if I put something on the table, the pressure might not be the same all underneath the kind of rectangular base of this iron wedge. Kind of looks like a simplified axe head here. If we do, the pressure is the force divided by the area. I don't want to use the whole area because the force is going to be sort of varying as we go across here. There's a huge one of these and we're going to lay on top of me. I'd want to lay under the left end, not the right end, right? That's where all the weight is going to be. So I could kind of divide this up into a bunch of pieces, right? These aren't the smallest pieces, but eventually I'm going to divide it up into more pieces than that. And for each piece, let's calculate the upward force from the table divided by the area of that piece. And that area is going to be, the area of this rectangular strip that's underneath the heaviest piece and so on to the left. If we do that, we'll find that the upward force from the table is really big at the right end because it's got a lot of weight on top of it, and it gets smaller in a linear fashion as you go to the left end. And so if we graphed the pressure as we went across it, the pressure would be increasing linearly. Now, I haven't really worried about where it starts out at here. Those of you who are used to thinking of the atmosphere would say, well, wait a minute, it shouldn't go down to zero there. There's actually quite a non-zero pressure over here, even though there's no metal hanging on top of it, because the atmosphere is just constantly hammering away at the table, right? All of those molecules drumming against the table are exerting a force on it, and there's an associated pressure. So maybe I should have started at a non-zero constant value, and then it would go up, and then it would drop down to that non-zero constant value once you're off that. The point is, it can just vary, and we're going to see that happens all the times with liquids and gases too. In the atmosphere, the pressure decreases as you go up. So for example, the pressure on the inner side of this glass cylinder increases as we go further down in the fluid. Okay, so we're going to find here we are above, we've got two different kinds of fluid here. There's a gas up here, atmospheric air, and then maybe I've got some water or something down here. And we're going to find that the pressure just due to the atmosphere, right? There's all these air molecules drumming against the inner surface of this glass. And that's exerting a force on the inner surface of the glass. Same thing's happening on the outer surface of the glass, but here we're just talking about the inner. And then once I start to go down in the fluid, it very quickly increases. So here we got kilopascals, thousands of pascals. So it's already a big pressure, at least on the scale of pascals, and then it's increasing quite a bit as we go down. And we're going to find out, or at least start thinking more and more in terms of the best way to think about that pressure when you have a fluid involved is just that you've got a bunch of molecules and they're constantly hammering against a surface. So if I sit here against the wall and I'm constantly punching it like this, the way some molecules might be doing, on average, I'm exerting a force trying to push the wall in that direction. And it's the same way with these molecules here, whether they're water molecules or a mixture of air molecules, they're drumming on the surface. Okay, so let's talk about some properties of pressure in fluids. And these are the kinds of things that hopefully you'll talk about at the beginning of lab, because I think Professor Lockett's class, they had their exam today, so they won't have talked about fluids at all. You guys will be a little bit ahead of the game, but I think I'm certainly, and I think Dr. Falco is also going to talk about pressure and density at the beginning. First property. We've been talking about pressure as if it's a force on a surface that's butting up against a fluid, but you actually don't need a solid surface in order for pressure to be defined. You can define the pressure in the middle of a fluid, right? So here in the middle of the air in the room, or in the middle of a glass of water at some point, okay? In other words, we can think of there being an imaginary surface here, and I've got some fluid on the right side of it and some fluid on the left side of it, and those molecules, maybe it's water, the water molecules are ramming into each other, right? And they're exerting forces on each other, and so the left-hand side is exerting a force on the right-hand side, and the right-hand side is exerting a force on the left-hand side. And just by thinking of things that way, there's a well-defined pressure here right in the middle of this water, even though I'm not near the edge of the container that's holding it. Okay, so pressure is something that's defined everywhere in the fluid. It's a little bit more confusing when you're not talking about the surface, but. Second property, if the fluid is in static equilibrium, okay, now static equilibrium we're going to take to mean no macroscopic flow. Of course, at the microscopic level, there's always lots of motion, right? The molecules are always jostling around. So we can't say everything's at rest. If we're thinking of the pressure as being due to molecular motion, then there's no such thing as not moving. But here we mean no overall flow of the fluid at the macroscopic scale, right? Individual molecules are moving, but whole sections of the fluid aren't turning over or moving. Then, surprisingly enough, the pressure doesn't depend on the orientation of the surface that you put there. In other words, you might think that if I held up a surface in the middle of a fluid, here we are in the middle of a fluid here, right? I put a surface here, and maybe the force would get bigger if I turn it this way, because look, all the weight is on top of it, right? Oh, look at all the atmosphere up there, right? Maybe the force gets bigger, and then maybe it gets smaller when I turn it in this direction or this way or something like that. But the answer, the point here is that that's not true, and we can sort of justify it with an easy thought experiment. So since it doesn't depend on the surface orientation, it does depend on the size of the surface. Well, it doesn't depend, the pressure doesn't depend on the size of the surface, but the force would get bigger as the surface gets bigger. But we don't care about the orientation, and therefore that's why we don't think of pressure as being something that has a direction. It's the same in all directions. Let's just think of a couple different cases, right? So here's a cube. It could be a cube of water in the middle of the water, or maybe it's actually a physical cube. It might be easier to think of it as a metal cube. Well, no, let's that won't work at all. Let's think of it as a cube of water down here, okay? And the fluid's at rest, so this cube's just sitting here. What would happen if the pressure on the right-hand side of this cube were different than the pressure on the left-hand side of this cube? Remember, I'm assuming the fluid's at rest. Why would that violate the assumption that the fluid's at rest? If the right-hand force on the right side of this imagined cube in the middle of the fluid were bigger than the left-hand force on the opposite side. Grant?
I'm trying to look at a better way of rationalizing this, but I want to say it's because like it's a force, even though it's scalar, or kind of is. I don't know how to word this properly.
Okay. Well, I mean, the pressure is associated with a force, but the question I guess I was asking is, how does it violate the assumption of static equilibrium, that the fluid is not flowing in the macroscopic level? Yeah, so Amelia is saying that if, for example, the right-hand force were bigger than the left side force here, then that cube is going to start accelerating toward the left, right? Because the right-hand force is winning out over the left-hand force, right? Here's a little, I'm just imagining in my mind dividing out a little cube of fluid. And somehow the adjacent fluid is pushing harder on the right than it is on the left. Let's do a small little piece of fluid. So the right hand and the left hand forces have to balance. The top and the bottom forces have to balance, and the front and the back forces have to balance on that little cube. Now that still doesn't tell, that tells us they have to balance left and right. But let's now imagine that even if the left-right forces balance and the top-bottom forces balance, but let's suppose the top and bottom forces were bigger in magnitude than the left and right forces. Why is that also going to violate the assumption here of the fluid being in static equilibrium, that it's not flowing? What would happen if the top and bottom forces were big and the left and right forces were small as time went on? Given that this is a cube of just liquid in the middle of liquid. Amelia? Well, it wouldn't start to sink. The suggestion was it would start to sink, but we're imagining the bottom and the top forces balance. And so nothing's pushing it down or pushing it up. So you may be a little bit, I'm imagining that this is such a small cube that maybe the mass of it is negligible. You know, it turns out if this is sitting on the surface of Earth, the bottom force is going to have to be a little bit bigger than the downward top force, because there's some additional weight force that's got to be balanced out by the bottom. We'll find that out later on. Let's imagine this is sitting in the space station or somewhere in deep space. There's no gravity. We don't have to worry about that. And suppose the left and the right force is balanced, the bottom and the top force is balanced, but the bottom and the top forces were twice as big as the left and the right forces. What would happen? Yes, Sarah? I don't think we'd have a net torque. In other words, it wouldn't cause it to start rotating like that, I don't think. Yeah, Edward Lee. Yeah, it would kind of flatten it. In other words, it would become deformed. The top and the bottom forces would say, I really want to push in this direction. And the side forces would say, well, we don't care so much if we like give a little bit. And therefore it would turn into a pancake if the top and bottom forces were big. And that would be a kind of flow, a macroscopic flow, right? Some little cube would get deformed, and we're not supposed to have shapes deformed. That's only true if it's at rest. If you got a cup of water and it's swirling around and turning over, that's not necessarily true. It still may be approximately true, but it's not absolutely true if it's moving. Okay, so therefore, just to wrap up this one, the pressure is independent of surface orientation. So we just say, I point to a point in space and I say the pressure of the gas, this fluid here that we're sitting in, there's a certain number. I don't have to tell you which orientation I put my surface. It's the same no matter what. Same thing with water. Third property, if the fluid's in static equilibrium, then the direction of the force associated with pressure, right? So pressure was defined in terms of a force, and we can think of the force associated with the pressure is perpendicular to the surface being considered. Okay, so I'm both, we could think of a water pressure force on the container that's holding the water, but also on adjacent bits of water if we're in the middle of the fluid. So let's try to see a nice picture about how to easily visualize that. Let's suppose so the claim is that the water right here at this piece of surface, this glass container, has to be pushing in the direction perpendicular to the surface. So it should be along the direction horizontal there. Let's suppose that the force from the water on the surface actually had a component which is parallel to the surface. That's drawn as F parallel here. So the force from the water on this tiny little bit of glass right here was sort of up and to the right. Can anybody think of why that would violate the assumption of static equilibrium at the macroscopic scale? We're assuming this water is just sitting there. This isn't true, again, if the water is turbulently turning over. We'll find out that it can look like this. But if the water is just sitting there, we can't have this vertical component of the force of the water on the glass. Edward Lee? Yes, why it has to be pointing exactly to the right, at least in this example picture here. Yeah, I know Zoom folks can't hear, but the answer I think that was given was something about it can't move the container. Although we'll find that, there's still, if I imagine swirling the water around so it starts moving in a circular fashion, circulating around the container, then it wouldn't be in static equilibrium. I could actually make it look like this. The force of the water on the container at that point could actually be non-parallel. The answer, since we're getting close to the end, and I want to maybe allow you guys to ask one more question. If the water's force on this little bit of glass here were along that diagonal direction, then by Newton's third law, the force of the glass on the water would have to be in this direction. Opposite, equal and opposite, right? And that means the glass would be exerting partly a downward force on the water at the surface, and that would cause the water to flow downward at the surface, or at least accelerate in the downward direction. Now, you kind of may have an intuition that the water kind of sticks to the surface. So it doesn't move really quickly at the surface, but it moves faster and faster as you get away. So if I started stirring this over and over, like really quickly in that direction, then the water is trying to pull the surface up, and it actually could pull in that direction. And that means the surface is trying to slow the water down by pulling it in the downward direction. That's one of the things that causes the water to stop turning after a while. It's that surface constantly pulling back on it. Okay, but if it's in static equilibrium, that's not allowed, and it's got to look like this, just everywhere perpendicular to the surface. So if, here there's fluid up here, it's a gas, right, presumably, then the direction has to be always perpendicular to the surface, outward in every case. Okay, and the last thing I'm not going to talk about, we'll derive it after break day, but the thing I just wanted to mention and that you're going to use in the lab is that the pressure beyond the atmospheric pressure that we're sitting in right now, we don't notice very much, increases with distance down in the fluid. And the formula we'll derive is delta P is equal to rho times G times H, where rho is the density of the fluid. And this formula is only true if the fluid is nearly constant density. Now, so when you have a glass of water, the density hardly changes at all. Even going to the bottom of the ocean, the density of water doesn't change that much. If you go up in the atmosphere, it changes quite a bit. But if I go down 10 feet in the air in the room, the density of the air doesn't change that much. So I can even apply this to air as long as I don't move through it too much. So H is how far you move downward in the fluid. G is the usual little g, and rho is the density of the fluid. If we were talking about air, it would be the local density of the air. If we were talking about water, it would be 1,000 in SI units. Okay, and we'll talk about the justification for that maybe after break day, after the exam and all that. Okay,